Good morning. Today, we're going to do one of my favorite subtopics, indeterminate form and L'Hopital's rule. Bernoulli, guy who invented the flow of wings, discovered that when you have a rational expression, as x goes to positive, negative infinity, this ratio can approach 0/0 or infinity/infinity. Then a guy named Guillaume L'Hopital, this is from Bernoulli, and then Guillaume L'Hopital then discovered that if I have a rational function and the limit of it as x approaches infinity, if it goes to 0/0 or infinity/infinity, then there has to be something in common with those two. At
So,
first, at first, I thought they'll just claim them as being undefined. But because they had something in common, we can find what they have in common together. Earlier in chapter 2, we took it algebraically. So for example, if we take the limit of x squared plus 5x plus 6 divided by x plus 3 as x goes to -3, we got 0/0. So what that showed us is if we factored out all the terms, and remove what they have in common, then our limit could be calculated as -1. But he went one step further. If the limit of a rational expression as x approaches some number a something that's undefined, then we can take the derivatives of the top and the bottom until the ratio doesn't equal 0/0. Right, which brings us to our first theorem, which we're going to be using for this section. Theorem 6, L'Hoptials rule. First off, if f of x and g of x are differentiable on the open interval AB, and our interval is inside we're looking at interval. So this a we're going to use C instead. So we're saying here is this. As long as the derivative of x does not equal 0 on that interval I, if x doesn't equal that letter A, then we will know this. The limit as x approaches that value A in that interval of our rational function is equal to the ratio of the derivatives. But we have to make sure first off that the two functions are differentiable, which means they're continuous on the entire interval, and the denominator is not equal to 0 on any value of the denominator of the interval. Example 1. The limit as x approaches 0 of 3x minus sine x over x. In chapter 2, what was the first thing we do? Nope. First thing we do is plug in 0. Three times 0 is 0. Sine of 0 is 0 over 0, so we get 0 over 0. If we get the 0 over 0, we plug in our value, then what we have to do is take the derivative. What's the derivative of the numerator?
3 minus cosine.
Very good. And the denominator? 1. Now let's plug in 0. 3 minus cosine of 0 over 1 is 3 minus 1 equals 2. The limit as x approaches 0, the square root of 1 plus x minus 1 remember, in chapter 2, we would have to multiply the top and bottom by the conjugate of the numerator. We have to multiply by square root of x, 1 plus 1 over square root of 1 plus x plus 1. That is too much work. So let's use L'Hopital's rule. First step, plug in 0. We got 0 over 0. Check. If it's not 0 over 0, we're done. We cannot use L'Hopital's rule. It has to be either 0 over 0 or infinity over infinity before we use L'Hopital's rule, or any combination thereof. 0 over infinity, infinity over 0. Has to have some sort of combination. First, always, yes. It has to be this, because if it's not that, if it's a number, you're done. Then the denominator of the derivative of the denominator is 1. So in the numerator, the derivative of the minus 1, this one's 0, so that one's gone. So we have the derivative of 1 plus x square root equals to 1 plus x to the power 1/2. So the derivative is 1/2. 1 plus x, subtract 1, so it's negative 1/2, times the derivative of the inside, which is 1. So the derivative of this minus 0 you don't do the quotient rule, because it's the derivative of the top, derivative of the bottom separately. Now let's plug in our values. So the denominator is 1, we don't need that. 2, 1 plus 0. 2 radical 1. 1 over 2 times 1 is 1/2. There's the limit. So think about it. Look back in your chapter 2 notes, so you find these same examples and see how long it took us to solve it. How many steps? Because we have to find the conjugate, multiply top and bottom, and go from there. And C, the limit as x approaches 0. Oh, because it's 0, 0, we call these functions indeterminate. They cannot be determined. So indeterminate, in other words, when you take the limit of something, it doesn't exist. So that's why these are called indeterminate. So plug in our value 0. We get 1 plus 0 is 1. 0 over 2 is 0. 1 minus 1. Okay, so it's indeterminate. This is indeterminate. Because it cannot be determined. Then I take the L'Hopital's rule. So the derivative of the top is the derivative of each of these parts separately. So the derivative of the first one we know is, we just calculated it. Minus the derivative of 1 is 0. And the derivative of x over 2 is 1 over 2. Over 2x. Why is the derivative of x over 2 1 over 2? X over 2 is the same thing as 1/2 times x. Take the derivative of x, you get 1. Answer is 1/2. Plug in 0. We got 1 over 2, 1 plus 0, minus 0 minus 1/2 over 2 times 0. One over 2 square root of 1. It's indeterminate again. So what do we do? Do it again. And again, so now we're taking the derivative of this equation. So you keep on doing it until you no longer get 1 over or 0 over 0.
So we're taking the second derivative?
This is now the second derivative. The derivative of 0 is 0, derivative of that's gone. So we have 1/2 1 plus x to the negative 1/2. Take the derivative of this, negative 1/2. 1 plus x, subtract 1 makes it negative 3 over 2. 1/2, so it's negative 1/4. It's negative, so it's on the bottom, but this is actually negative 1/2. So since this is a fraction, that 1/4, so it's negative 1/4 times 2. So we got negative 1/1 plus x square root of 1 plus x over 8. Plug in 0. 1 plus 0, square root of 1 plus 0. One square root of 1. Negative 1/8. It's all algebra. Since we were going to 0, I should have left it as negative and put it on the bottom. I should have made this 1 plus x to the 3/2 on the bottom. Oh well. Just get the same answer. One more. D. The limit as x approaches 0 over x cubed. L'Hopital rule only works on rational functions, fractions. So the first thing is plug in your 0. 0 minus 0 over 0. It's indeterminate. Then we take the derivative of top and bottom. Derivative of x is 1. Derivative of sine is cosine. Derivative of x cubed is 3x squared. Plug in 0. Cosine of 0 is 1. 3 times 0 is 0. It's indeterminate again. So we take another derivative. as x approaches 0. The derivative of 1 is 0. Derivative of cosine is negative sine over 6x. Negative makes me a positive, so it's positive sine x over 6x. We could finish here, but I'll show you why. We could finish here. I'm gonna put a box here. If we put in 0, we get sine of 0. 6 times 0 is 0 over 0. So it's indeterminate again. Then again. So we take the derivative of this one. Derivative of sine is cosine. Derivative of 6x is just 6. Cosine at 0 is 1 over 6. The answer is 1 over 6. Okay, remember I told you here we could have stopped and gotten the same answer. Anybody know how? We had limit as x approaches 0, sine x over 6x. Now, we can rewrite this one as 1 over 6 times sine x over x. Constant multiple goes out in front. The limit of sine x over x is 1. We learned that in the first part of chapter 2. So the answer is 1 over 6. Example 2. The limit as x approaches 0 of 1 minus cosine x over x plus x squared. What's first step one?
Plug in 0.
Plug in 0. So we get 1 minus cosine of 0, 0 plus 0 squared. Cosine of 0 is 1. 0 plus 0 is 0. So we get 0 over 0. So it's indeterminate, which means we can use what? L'Hoptials. So take the derivative of the top and bottom separately. Derivative of 1 is 0. Derivative of cosine is negative sine x. Very good. Derivative of x is 1. Derivative of x squared is 2x. Which gives us negative and negative is positive, so it's sine x over 1 plus 2x. Plug in 0. Sine of 0 is 0. 2 times 0 is 0. So we get 0 over 1. So what do we do? I don't know. What do y'all think? Let's take a meeting of the minds.
Well, it's not 0.
So we can't keep on going. So the answer is, yeah, 0 over 1 is 0. That's the answer.
So it can't equal 0 over 0 or infinity over infinity, but can equal 0 over whatever number.
Yeah. Or is if the top or bottom become non-zero, you can't, or non-infinity, you can't go any further. If it's 0 over 1 or 1 over 0, you can't go any further. You're done. Example 3. The limit as x approaches 0 from the right sine x over x squared. So first step, plug in zeros. Sine of 0 over 0 squared is 0 over 0. Indeterminate. So take the derivative. Derivative of sine is cosine. X squared is 2x. Cosine of 0 over 2 times 0. So what's the answer?
Infinity.
Positive infinity. Because remember, we're going to 0, 0 from the right. Our vertical asymptote is 0, is the x-axis. So as our value gets closer to 0, it goes to positive infinity. So that's our answer.
So odd question here.
Yes.
So in aviation, we learn Bernoulli's principle, but
Right.
it only works up until supersonic where it flips. Is this what describes that, or is that something else?
That's something else.
Okay.
But yes, it will relate similar to this. But yes, it's because when it reaches supersonic and hypersonic, it flips because of the dynamics of the wing, the nose and the wings now become less important. It's now just flying a missile. Because Bernoulli's principle depends on the air around the wing. Right. And what happens is as the sound wave approaches, it comes off the wing. So if we look at an airplane, the wind goes around the wing plane like this and over the wings. But as we get faster and faster, it gets closer and closer to the fuselage, which is why hypersonic jets all have delta wings. case in point, the space shuttlecraft at the hypersonic, supersonic speeds, longer wings would be just extra dead weight. Wouldn't do anything for it.
Be harder. to get to the speed.
Right.
Oh, it's like a pump. The tire scientists knows that,
Exactly, like the Pilgrim Falcon. It puts his wings next to its body, make it more streamlined, more aerodynamic. It just becomes a missile at that point. And the X-15, it was just a missile with very short, stubby wings. Because at supersonic and hypersonic speeds, it's not going to matter much how the wings. Now let's look at the same equation from the other side. We get 0 over 0. So we take the derivative of it. This time we're looking for x's coming from the left. This is going to be cosine x over 2x. Cosine as approaches from the left. From the right. This one's going to equal negative infinity. So far we've looked at 0 over 0. But what about infinity over infinity, infinity over 0, infinity times 0, or infinity minus infinity? The question you're going to ask is, well, why didn't we do that in example 2? Or was that example 2? Yeah. What about this? Because this came to an integer, a countable number. We're looking at specifically at infinity or zeros. If it's other than that, then we can use L'Hopital's rule. It doesn't exist. If it becomes a number, we're done with that. So we have the limit as x approaches pi over 2 of secant x over 1 plus tangent. Our first step is just plug in our value. Secant of pi over 2, 1 plus tangent pi over 2. So what is secant at pi over 2? If you don't remember, then secant is made up of what? And tangent is made up of? So what is cosine at pi over 2? Zero. So it's 1 plus sine of pi over 2 is 1 over 0. So what is 1 over 0?
Infinity.
Infinity. 1 plus infinity. So this equals infinity over infinity. So we can use L'Hopital's rule here. Because it's indeterminate. We can't get a number. So the limit as x approaches pi over 2 derivative of secant is secant tangent. Are you guys sure I didn't give you those formula sheets?
I remember you talking about it.
Okay, I'll make it myself. I will send it to you all in a remind as well as make
Yeah, as I
copies.
said, I know there's some under mind. I just printed a couple off.
Okay, yeah, those are the ones. Yeah, so you have those. It's on. I sent it. It's also on the syllabus on the online. But I'll give you all a hard copy tomorrow. The derivative of 1 is 0. The derivative of tangent is secant squared. X. So x approaches pi over 2. Well, when one of the secants can cancel. So we have tangent x over secant x. So we get sine over cosine over 1 over cosine, which becomes sine x over cosine times the flip of the bottom. One. Cosines disappear. So we have sine at pi over 2 is 1. All I did, if you know your trig functions, we know that tangent at pi over 2 is 1. And secant at pi over 2 is also 1. Because it's 1 over cosine, well, that's infinity. But yeah, that's why it's much easier if we go ahead and do that. I like to change everything to sine and cosine. Take the top, leave it alone, flip the bottom. Cosines cancels, so we're left with sine x. Sine x, when x goes to pi over 2, is 1. And B. The limit as x approaches infinity natural log of x to square root of x. All right, so what do we do first? Plug in our value at infinity. So we have ln at infinity, the square root of infinity. What's the ln at infinity? So it's infinity over infinity. Remember, the ln function looks like this. As x gets larger, it goes higher, so it goes to infinity. So we can use L'Hopital's. The derivative of ln x. The derivative of ln u is 1 over u du. So this becomes 1 over x. And the square root of x is x to the power 1/2. The derivative of it is 1/2 x to the power negative 1/2. So it's 2 times 1 over 2 square root of x. The 2's cancel. The limit as x approaches infinity. Take the top fraction, leave it alone, multiply by the reciprocal of the bottom. So we get square root of x over x, which leads us to one over square root of x. Because what is the square root of x times square root of x? Is square root of x squared, which is x. So this number is the same as square root of x square root of x. I can cancel those out. As x goes to infinity, what do we get? What is it equal? What's the limit going to?
Say that again.
This and this one here. As x goes to infinity, what is 1 over square root of x? What is, let's look at the graph 1 over x.
Oh, it's going
What
to
does the
zero.
graph look like? When x goes to infinity, where is my y value going?
0.
Because as the bottom gets bigger, the number gets smaller. And then C. Another one to infinity. E to the power x over x squared. So our first step, e to the power infinity is infinity, infinity squared is infinity, so we can use L'Hopital's rule. The derivative of e to the x. Remember the derivative of EU du. So it's just e to the x, derivative of the exponent is 1, over 2x. So we get e to the infinity over 2 times infinity. We got infinity over infinity. So we get to do it again. Derivative of the top is e to the x, the derivative of the bottom is 2. So it's e to the infinity over 2. Infinity over 2 equals infinity. I'm not gonna, it's gonna take practice to make sure you understand all these steps and all these rules. But it's practice that you have to do. Example 5. Now we're gonna look at limits of infinity times 0. As x goes to infinity, we got x times sine of 1 over x. As we plug in our values, so it's infinity times sine of 1 over infinity. The sine of 1 over infinity is 0. Infinity times 0 does not necessarily equal 0. So we take the derivative. We have a product rule. So it's x sine of 1 over x. The derivative of x is 1. The derivative of sine 1 over x. Derivative of sine is cosine times the derivative of the inside. The derivative of 1 over x is negative 1 over x squared. So we get sine of 1 over x times 1 minus x times negative 1 over x squared cosine 1 over x. See? It's all one unit. So it's sine x 1 over x. I don't know if I put a dividing line there. Negative and negative makes it a positive. X over x squared makes it 1 over x times cosine 1 over x. Sine at 1 over infinity plus 1 over infinity times cosine of 1 over infinity. Minus plus to quotient, so that's a minus sign. So that becomes 0. One over infinity. Okay, hold it. X sine 1 over x. So derivative is 1. Cosine 1 over x. Derivative of 1 over x is negative 1x squared. X negative 1 squared times cosine. Sin x times x. Okay. So this is 0. That's very small, so it's 0. Okay, I'm trying the other way here. X sine 1 over x. Here, that's the part that's giving us trouble. So h is 1 over x. So this is as x goes to infinity. X is 1 over h. Sine h. So that's 1 over x. Much easier if we did it this way, a substitution. So we have sine h over h, which is 1 from chapter 2. I mean, it should have worked, but we had these issues here. So there's your answer, 1. It's B. Radical x ln x. So yeah, it's much easier if you use substitution. Skip that. Because we had a rational. Limit as x approaches 0 from the right of radical x ln x. Why is it from the right only? Which one? Both of them.
The positive?
Rational is that. And then ln x is this. So we can only approach 0 from the right. All right. So we're on 0. So if we plug in 0, what do we get? Square root of 0, ln of 0. Square root of 0 is 0. ln of 0 is infinity. It's actually negative infinity, but it's still an infinity. So we have 0 times infinity. I want to try the product rule first. If that doesn't work, then we'll use the conversion formula. Yeah. 1/2 square root of x on top ln x plus square root of x over x. Infinity over 0. So here we have x ln x plus 2x over 2x square root of x. Yeah, that's going to lead us down another path much further. So if we have 0 times infinity and it leads us to a complex function like this, convert this to a rational, either 0 over 0 or infinity over infinity. Since we have an infinity here, since ln x as x goes to 0 goes to infinity, although it'd be negative infinity, this one goes to 0, convert that one. So square root of x is the same thing as 1 over square root of x. Because it's a rational function. Take the top, leave it alone, flip the bottom. So now we have infinity over infinity. We have 1 over 0. Why is that good? Because now we can take the derivative and we know it's going to work. It's going to be much simpler. Because we only have one function here and one function down here to worry about. So the limit as x approaches 0 from the right, the derivative of the top is 1 over x. And 1 over square root of x can be written as x to the power negative 1/2, which the derivative of it makes it negative 1/2 x to the power negative 3/2, which is on the bottom. Now we can rewrite these. Take the top fraction, leave it alone. This bottom one is -1 over 2x 3/2. Flip that, we get 2x to the 3/2 over -1. Again, this is just algebra. So the answer is going to be -2. So we have x to the 3/2 divided by x, which is x to the 3/2 divided by x to the 2 over 2. Subtract the exponents, we get 1/2 on top. -2 square root of x. -2 times 0. All that for 0, but nothing. So why did we do what we did? Because we have a property that says if we have infinity times infinity or 0, if it works, it's great. So it's, those are saying, if you get infinity times 0, try to convert it to infinity times infinity over infinity. Because what makes it 0, if you put it on the bottom, you have to flip it. So now 1 over 0 is now infinity. Because this is 0 over 1. If I put it on the bottom, it's now 1 over 0, which makes it infinity over infinity. Once we have it that, then we use L'Hopital's rule. Let's look at example 5. Now we have another property here that looks at example 6. So where's the example? There it is. We're looking at infinity minus infinity. As x approaches 0, 1 over sine x, 1 over x. Infinity minus infinity. So check, we got that. So let's do L'Hopital's. Before we do L'Hopital's, we have to combine them. Remember, L'Hopital's rule is f of x over g of x. And so we have two separate functions. So we have to combine them. This side needs an x over x. This side needs a sine x over sine x. So sine x times x is on the bottom. X minus sine x. And we get 0 over 0, which is what we're looking for. Because once we get 0 over 0, now we can use L'Hopital's rule. The derivative of x is 1. Derivative of sine is cosine. Now we don't have a choice, but we have to use the product rule. We have x times sine x. 1 times cosine. Which makes it sine x plus x cosine x. Plug in our 0, cosine of 0, sine of 0, plus 0, cosine of 0. 1 minus 1, 0 plus 0. So we got 0 over 0 again. So we got to take the derivative again of the quotient rule. So f of x is 1 minus cosine x. G is sine x plus x cosine x. Derivative of 1 minus cosine, that's 0. Derivative of cosine is negative sine. That equals positive sine. Derivative of sine x is cosine. Plus the derivative of x cosine. So we have x cosine x 1 negative sine x. So it's going to equal cosine minus x sine, which equals 2 cosine minus x sine x. Woo! So the derivative of the top is 0 minus negative sine. The derivative of the bottom is 2 cosine minus x sine. It was just straight down. These are my derivatives, numerator and denominator. So the top is just sine x, 2 cosine x minus x sine x. Plug in 0. Sine of 0, 2 cosine of 0 minus 0 sine of 0. Cosine of 0 is 0. No, sine of 0 is 0. Cosine of 0 is 1. So the answer is 0 over 2, 0. It's not difficult, it's just long. A lot of moving steps. Again, you have to know how to do your derivatives. What about next part is indeterminate powers. In other words, looking at when we get the form 1 to the power infinity, 0 to the power 0, or infinity to the power 0. After we take the limit, we get this. Again, Hoptials. Where's, should I put that? Well, here's what it looks like. If the limit as x approaches a of ln x, or ln of a function of x, equals L, then the limit as x approaches a of f of x equals the limit of e to the power ln f of x equals e to the power L. And that's what we're going to be using here. Example 7. Okay. Show that the limit as x approaches 0 from the right of 1 plus x to the power 1 over x equals e. So this is going to be our f of x. Okay, so as we said here, so if that's our f of x, then the ln of f of x, and the limit of the ln of f of x as x approaches 0 from the right becomes the limit of ln of our function 1 plus x to the power 1 over x. Why do we do the ln? Because what's one of the properties of natural logs? We're just looking at this right now. What can we do with that? You cannot have exponents, so the exponent comes out in front. 1 over x dx. Yeah. So now what we have is the limit as x approaches 0 of 1 over x ln 1 plus x, which gives us, oh, this is from the right only, ln 1 over x over x. If we plug in 0, what do we get? We get ln of 1 over 0. What is the ln of 1? Remember, the graph of the ln function, if x is 1, y is 0. It crosses the x-axis at 1. So we got 0 over 0. So what does that tell us to do? L'Hopitals. It's much easier to take a derivative of this function than it would be this one. So the limit as x approaches 0 from the right. What's the derivative of ln x? Yeah, so it's 1 over 1 plus x dx, which is just 1. What's the derivative of x? So we got the limit as x approaches 0 from the right of 1 over 1 plus x. Plug in 0. Our value is 1. So if that's the limit, so remember, what we're looking for originally was show that this 1 plus x, we're supposed to show this. And using this part, limit of fx is the limit of e to the power ln, whatever that is simply e to the power l. So whatever our limit was, that goes up here. So show we get that the limit as x approaches 0 from the right of this, this is our f of x. Remember, our f of x was 1 plus x to the power 1/2. So that means we can take our function, make it as an exponent. So this is e to the power what was the limit of this function here? So it's e to the 1, which is just e. So what did this example just show us? If you're given a function like this, do it in 2 parts. You have to first find the limit of this function as far as it can go. Once you find that, that's going to be, whatever this is, will be the exponent of this. So whatever you get there, plug it in there. And that's your answer. Find this limit as x goes to infinity of x to the power 1/4. No, x, 1x, I'm sorry. X to the power 1 over x. Is this similar to the last one? Yeah. Because whatever we get here, when we find the limit of this one, whatever that is the exponent of our e. So the first thing we do is what? What do we know about this one? X over 1 over infinity. 1 over infinity becomes what? Yeah, because it gets very big, so it's. And when x goes to infinity, we get infinity to the power 0. So what is our f of x? X to the power 1 over x, right? Now we got to find the limit as x approaches infinity of ln f of x. Here's a question again, algebraically, why do we use the ln function? Because the variable is an exponent. The ln function brings it out in front. Take the numerator exponent down, make it a coefficient. So whenever you have a variable that's an exponent, take the ln of it. So what we have here is x to the power, x to go to infinity of ln x to the power 1 over x, which gives us the limit as x goes to infinity of 1 over x, because this thing goes out here. 1 over x ln x, which is the limit as x goes to infinity of ln x over x. As we go into infinity, what happens? Limit at ln at infinity is what? Infinity over infinity. So we could use L'Hopital's rule. So the limit as x goes to infinity, the derivative of ln x is 1 over x. Derivative of x is 1. So the limit as x goes to infinity of 1 over x becomes what? Zero. So what that means, we know what's going to happen, all this sort of stuff, is we have e to the 0, which is 1. That's our answer. But where did that come from? That came from the limit of e to the power ln x to the power 1 over x. So that's our answer we're looking for, 1. All right, that's it for that. On time today. Actually, 10 minutes late. So again, L'Hopital's rule is one of my favorite parts of calculus because it's makes it much easier. But you have to make sure that whatever form you have, if it's infinity times infinity, infinity times, you have to put it as a fraction. In order to use L'Hopital's, it's got to be 0 over 0, infinity over infinity. Do whatever you need to do that, and then take derivative. All right. That's